Picture this: you're standing beneath a vast, starlit sky, gazing at billions of shimmering stars. Each one holds the promise of countless worlds. What if, on one of those distant planets, someone is looking back, wondering the same thing? Are we alone in the universe? This question is one of humanity's most profound mysteries. It has captivated philosophers, scientists, and dreamers for centuries. But unlike philosophical debates that often end in speculation, the search for extraterrestrial life led to a scientific approach, one that gave rise to the Drake equation. The Drake equation, created in 1961 by astrophysicist Dr. Frank Drake, is a formula that seeks to estimate the number of intelligent civilizations in the Milky Way galaxy. It's a simple equation with complex implications, serving as a beacon for astronomers and inspiring generations of thinkers to ponder our place in the cosmos. But what makes the Drake equation truly fascinating is not just its math, it's the profound questions it forces us to confront. What are the odds that life exists beyond Earth? How likely is it that intelligent civilizations develop the technology to communicate? And if they do, why haven't we found them yet? In this video, we'll break down the Drake equation, explore its components, and discuss its implications for humanity. By the end, you'll not only understand the science behind this formula but also why it continues to inspire our search for extraterrestrial life. Let's travel back to 1961. The world was in the midst of the space race, with the United States and the Soviet Union competing to explore the cosmos. In this era of innovation and curiosity, Dr. Frank Drake was preparing for a historic scientific meeting. This gathering, held at the Green Bank Observatory in West Virginia, was the first of its kind to focus on the scientific search for extraterrestrial intelligence, SETI. Dr. Drake faced a challenge. How could he guide the discussion and provide a framework for exploring the possibility of alien civilizations? The answer came in the form of a groundbreaking formula, now known as the Drake equation. N equals R underscore asterisk backslash times F underscore P backslash times N underscore E backslash times F underscore L backslash times F underscore I backslash times F underscore C backslash times L. Here's what it represents. N, the number of detectable civilizations in the Milky Way. R asterisk, the average rate of star formation in our galaxy. F underscore P, the fraction of stars that have planets. N underscore E, the number of planets per star that could support life. F underscore L, the fraction of those planets where life emerges. F underscore I, the fraction of planets with life where intelligent beings evolve. F underscore C, the fraction of civilizations that develop detectable technology. L, the length of time these civilizations release detectable signals. What made this equation revolutionary wasn't its precision, it was its ability to spark curiosity and scientific inquiry. Dr. Drake himself described it as a way to organize our ignorance. Breaking down the variables. To truly appreciate the Drake equation, we need to understand its components. Let's begin with the first few variables, which set the foundation for estimating the odds of intelligent life. 1. The rate of star formation, R asterisk. The journey begins with the stars. How many stars form in the Milky Way each year? Modern estimates suggest this number is around 1 to 3. This rate is influenced by the galaxy's structure, the availability of star-forming material, and the presence of regions like the Orion Nebula, where star formation is particularly active. 2. Fraction of stars with planets, F underscore P. For most of history, we didn't even know if other stars had planets. But thanks to groundbreaking missions like NASA's Kepler Space Telescope, we now know that planets are incredibly common. In fact, nearly every star is likely to host at least one planet. This discovery has fundamentally changed our understanding of the cosmos and significantly increased the value of 3. Habitable planets, N underscore E. Not all planets are created equal. To support life, a planet must meet certain criteria, the most important being its location in the habitable zone. This is the region around a star where conditions allow liquid water to exist, a crucial ingredient for life as we know it. Consider Earth's place in the solar system. Too close to the Sun, like Venus, and water boils away. Too far, like Mars, and it freezes. But just right, and you have the Goldilocks zone, a sweet spot for life. Current estimates suggest that around 20 to 25% of stars have planets within their habitable zones. This means there could be millions, if not billions, of potentially habitable planets in our galaxy alone. Real-world example. One famous example is Kepler 452b, a planet located about 1,400 light-years away. Often called Earth's cousin, it's similar in size to Earth and orbits its star in the habitable zone. 4. Fraction of planets where life emerges, F_L. Here's where the Drake equation begins to venture into speculative territory. Even if a planet is located in the habitable zone, how likely is it for life to emerge? On Earth, life appears to have begun relatively quickly after the planet's formation, around 3.8 billion years ago. This rapid emergence suggests that, given the right conditions, life might not be an extraordinary event. However, there's a catch. Earth is the only data point we have. Could it be that life is rare, even on planets with favorable environments? Or is life an inevitable outcome of chemical and physical processes? The role of extremophiles. Extremophiles, organisms that thrive in extreme conditions, give us clues about life's resilience. From microbes living in acidic hot springs to bacteria surviving deep in Antarctic ice, these hardy organisms suggest that life could exist in environments previously thought to be inhospitable. Example from Mars exploration. Mars rovers like Perseverance are searching for signs of past microbial life. If we find evidence of even simple organisms on Mars, it would revolutionize our understanding of, showing that life can arise independently in multiple places within a single solar system. 5. Fraction of life that becomes intelligent, F_I. Let's say life does emerge. How often does it evolve into intelligent beings capable of complex thought, problem solving, and technological innovation? Here's the sobering truth: intelligence may not be a guaranteed outcome of evolution. Earth's history provides a striking example. Life existed for billions of years before the appearance of humans. Even among Earth species, intelligence on the level of humans is exceedingly rare. Consider dolphins, octopuses, and crows, animals with remarkable problem-solving abilities. Yet none have developed civilizations or technology. This raises a critical question: is intelligence a fluke, or is it an evolutionary advantage that nature is likely to replicate elsewhere? The anthropocentric bias. One challenge in estimating is overcoming our bias as humans. We tend to assume that intelligence is the pinnacle of evolution, but nature might favor simpler, more adaptable organisms. After all, bacteria have been the most successful form of life on Earth for billions of years. 6. Fraction of civilizations that develop detectable technology, F_C. Intelligence alone isn't enough. For a civilization to be detectable, it must develop technologies like radio signals, lasers, or spacecraft that we can observe from Earth. The invention of radio waves on Earth marked a turning point. For the first time in our history, we became visible to the cosmos. But this also introduces a significant variable: how many intelligent civilizations develop technology that emits detectable signals? Case study: the WOW signal. In 1977, astronomers detected a mysterious radio signal known as the WOW signal. It lasted for 72 seconds and has never been observed again. While it remains unexplained, it highlights the tantalizing possibility that extraterrestrial civilizations might try to communicate using radio waves. 7. Longevity of detectable civilizations, L. This is perhaps the most sobering and uncertain variable in the Drake equation. A civilization must remain detectable long enough for us to find it. Humanity has been broadcasting signals for about 100 years, a blink of an eye on cosmic timescales. Will we continue to emit signals for thousands of years, or will we go silent due to self-destruction, technological shifts, or environmental collapse? The Fermi paradox. This leads us to the Fermi paradox, which asks, if intelligent civilizations are common, why haven't we found any evidence of them? One possible answer lies in: civilizations may be short-lived, destroyed by war, climate change, or other factors before we can detect them. Optimistic perspective. On the other hand, some theorists believe advanced civilizations might deliberately avoid broadcasting their presence, choosing to remain undetectable to protect themselves from potential threats. The range of possibilities. When scientists plug optimistic values into the Drake equation, they arrive at a staggering result: there could be thousands of advanced civilizations in the Milky Way. But when conservative estimates are used, the number shrinks to just one, us. This vast range underscores both the power and the limitation of the Drake equation. It provides a framework for exploration but relies heavily on our assumptions about life, intelligence, and technology. The implications of the Drake equation. The Drake equation does more than estimate numbers; it fundamentally shifts how we perceive ourselves and our place in the cosmos. If intelligent life is abundant, it means humanity is part of a vast, interconnected galactic community. 2. Impact on technology and exploration. The Drake equation has fueled decades of scientific innovation. It has inspired projects like the SETI Institute, which uses powerful radio telescopes to search for extraterrestrial signals. It also motivates missions like the James Webb Space Telescope, designed to analyze the atmospheres of exoplanets for signs of life. Example. In 2015, the Breakthrough Listen initiative, funded by entrepreneur Yuri Milner and supported by physicist Stephen Hawking, dedicated $100 million to the search for extraterrestrial intelligence. This project embodies the hope and determination sparked by the Drake equation. Criticisms of the Drake equation. While the Drake equation is a powerful tool for organizing our thoughts, it is not without its flaws. Critics argue that its variables are too uncertain, making its results more speculative than scientific. 1. Lack of empirical data. Many variables in the Drake equation, such as n, are based on educated guesses rather than hard data. For instance, while we know planets are common, we still have no evidence of life beyond Earth. 2. The assumption of universality. The equation assumes that life and intelligence evolve similarly throughout the universe. But what if alien life operates under principles we can't even imagine? The variables in the Drake equation may not fully capture the diversity of possibilities. 3. Technological bias. The equation also assumes that civilizations communicate using technology we can detect, like radio waves. Advanced civilizations might use communication methods far beyond our understanding, making them effectively invisible to us. The Great Filter Hypothesis. One of the most thought-provoking ideas related to the Drake equation is the Great Filter Hypothesis. This concept suggests that there's a stage in the evolution of life that is incredibly difficult to pass. 1. Where is the filter? The Great Filter could occur at various stages. The emergence of life might be extraordinarily rare, requiring a perfect storm of conditions. The development of intelligence, even if life arises, the evolution of intelligent beings might be exceedingly unlikely. The survival of civilizations, intelligent civilizations might self-destruct through war, environmental collapse, or other crises before they can explore the stars. 2. What it means for us. If humanity has already passed the Great Filter, it could mean we're incredibly fortunate, a cosmic anomaly. But if the filter lies ahead, it suggests that the challenges we face, such as climate change and nuclear proliferation, are universal threats to intelligent life. The search continues. Despite its uncertainties, the Drake equation remains a cornerstone of the search for extraterrestrial life. Scientists and enthusiasts alike continue to refine its variables and explore new avenues for discovery. 1. Exoplanet exploration. Since the Drake equation was first proposed, our understanding of exoplanets has grown exponentially. The discovery of thousands of exoplanets, many in the habitable zone, provides a tantalizing hint that life might be more common than we once thought. 2. Technological advancements. Projects like the Square Kilometre Array, SKA, set to be the world's largest radio telescope, promise to revolutionize our ability to detect distant signals. Meanwhile, advancements in artificial intelligence are enhancing our ability to analyze vast amounts of astronomical data. Real-world progress. In 2020, astronomers detected phosphine gas in the atmosphere of Venus, a potential biomarker for life. While the discovery remains controversial, it highlights the growing sophistication of our search methods. Philosophical questions raised by the Drake equation. The equation doesn't just challenge our scientific understanding, it also raises profound philosophical and ethical questions. 1. If we're not alone. How should we respond if we detect extraterrestrial life? Should we attempt to communicate, or would that risk exposing ourselves to potential threats? 2. If we are alone. If humanity is the only intelligent civilization, what does that mean for our purpose? Does it amplify the importance of preserving our planet and ensuring the survival of our species? The role of hope and imagination. Ultimately, the Drake equation is not just about numbers, it's about hope. It represents humanity's desire to connect, to understand, and to explore. Whether we find evidence of alien life or simply expand our understanding of the cosmos, the journey itself is profoundly meaningful. Looking ahead, the future of the Drake equation. The Drake equation isn't just a relic of 20th century science, it's a living framework, continuously evolving as our knowledge grows. The next few decades promise breakthroughs that could refine its variables and even provide answers to some of its most perplexing questions. 1. Refining the variables. Advancements in telescopes, such as the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, are helping us analyze the atmospheres of exoplanets for biosignatures, chemical markers that indicate life. Molecules like oxygen, methane, and water vapor, detected in the right combinations, could signal the presence of life. 2. Exploration of moons and planets. Missions to icy moons like Europa and Enceladus are poised to search for microbial life beneath their subsurface oceans. These environments, shielded from harsh space radiation, could host ecosystems similar to Earth's deep-sea hydrothermal vents. Example: NASA's upcoming Europa Clipper mission aims to investigate whether Europa's subsurface ocean could support life. A positive finding would profoundly impact our understanding of 3. The role of artificial intelligence, AI. AI is revolutionizing our ability to sift through vast datasets. In the search for extraterrestrial intelligence, SETI, AI algorithms are being used to detect subtle patterns in radio signals that could indicate intelligent communication. Cultural and philosophical impact. The Drake equation has transcended its scientific origins, becoming a cultural touchstone that fuels our collective imagination. Its influence can be seen in science fiction, art, and even religion, as humanity grapples with the profound implications of its variables. 1. Science fiction and popular culture. From Carl Sagan's Contact to movies like Interstellar and Arrival, the search for extraterrestrial intelligence has captured the public's imagination. These works explore themes of communication, isolation, and the nature of intelligence, ideas rooted in the Drake equation. 2. Religious and philosophical reflections. The possibility of alien life raises deep questions about humanity's place in the universe. Some religious perspectives view the existence of extraterrestrial civilizations as an extension of divine creation, while others wrestle with the theological implications of non-human intelligence. 3. The unity of humanity. One of the most profound aspects of the Drake equation is its ability to inspire a sense of unity. The search for extraterrestrial life transcends national borders and cultural differences, reminding us that we are all inhabitants of the same fragile planet. Challenges and ethical considerations. The search for intelligent life isn't without its ethical dilemmas. What responsibilities do we have if we find evidence of extraterrestrial civilizations? 1. Communication risks. Physicist Stephen Hawking warned that broadcasting our presence could be risky, comparing it to Native Americans encountering European explorers. Should we focus on listening rather than transmitting? 2. Preserving biospheres. If we discover microbial life on Mars or Europa, should we prioritize exploration or preservation? The ethical questions surrounding contamination and exploitation of alien ecosystems are increasingly pressing. A cosmic journey without end. The true power of the Drake equation lies in its ability to inspire exploration and wonder. Even if we never find definitive evidence of extraterrestrial life, the pursuit itself deepens our understanding of the universe and our place within it. A thought-provoking question. As we gaze at the stars and ponder the Drake equation, one question lingers: if the cosmos is vast enough to support countless civilizations, why haven't we heard their voices yet? Is it because we haven't listened carefully enough, or because they're waiting for us to take the next step? Closing remark. In the end, the Drake equation is more than a mathematical formula. It's a reminder of humanity's endless curiosity. Whether we're alone in the universe or part of a galactic family, the journey of discovery unites us all. So, let's keep searching, listening, and imagining what lies beyond.